Let's see. Well, yeah, we'll get started now. I think it's a good time, although there are still some people arriving. Hello, everyone. Thank you for being here. I'm Dave Halsing, and with me is my colleague Donna Ball and our guest speaker today, Michael MacWilliams. Thanks for attending this last in our year-long Lunch and Learn speaker series. It's been a fun ride. We've gotten a lot of positive feedback on it, and I think it's been worth doing. So we're all up to date now. Like we've covered almost all the big topics that we have in process. And so we'll be taking a break for a year or two to let some more work get done and that we have, some more completed work and meaningful findings to report. So, but we're going to go out with a bang today with our speaker for this month's Lunch and Learn, Dr. Michael MacWilliams. He'll be presenting his modeling and analysis work that was done in support of the Valley Water-led San Tomas Aquino Calabazas Creek-Marsh connection project. That is a mouthful. We don't usually use the full name. That project, as I mentioned, led by Valley Water. The restoration project team has been collaborating with Valley Water really the whole time on the development of that project. A lot of it is on National Wildlife Refuge lands, and in the footprint of the Salt Pond Restoration Project, it would advance about 1,400 acres of tidal marsh restoration in some of those former ponds, and we would otherwise have to do it ourselves. So we're grateful to Valley Water for taking the lead role on these early steps in it. It's important to them to reconnect those two creeks to the tidal marsh restoration, both for their flood risk management responsibilities and also to reduce the maintenance needs in those two creek channels. Michael is part of a large and diverse consultant team working on the projects. We won't have time today to discuss all of the different pieces of work that they've done. We're really trying to focus this one on Michael's work and his presentation, which is titled Building Ecosystem Resilience Through Reconnecting Sediment Supply from Creeks to Tidal Wetlands. He's going to tell us about the project's location goals, the project so far, the future plans, and then dive in more detail on the actual modeling and the results and what they mean for the project. But first, I need to introduce him. Michael MacWilliams is a principal engineer at FlowWest. He's been consulting around San Francisco Bay for over 25 years. His PhD at Stanford University focused on the application of detailed three-dimensional hydrodynamic modeling to models to flow in river channels and floodplains to improve river restoration project designs and implementation. He's developed and applied 3D hydrodynamic wave, salinity, temperature, sediment transport, and morphologic models in large estuaries for all of these years, publishing almost 30 papers on those topics. This sounds prestigious, even though I don't know who these two people are, but he is a recipient of the Lawrence G. Straub Award and the Hugo B. Fisher Award. So, Michael, if you have time at the end, you should tell us who those people were and why they have awards named after them. Finally, on a personal note, he's an extraordinarily pleasant person to work with and an excellent presenter. So sit back, enjoy the presentation, get your questions ready for Q&A either at the end or you can drop them into the chat box as we go. And with that, I will stop talking and leave you in the competent and capable hands of Michael MacWilliams.
Thank you, Dave. So today I'm going to be talking about building ecosystem resilience through reconnecting sediment supply from creeks to tidal wetlands. Before I dive into the talk, I just want to talk a little bit about this first image because it provides some context for what I'll be talking about today. So I'm not sure, do you guys see the cursor on the slide? Yes, okay. So these ponds down here at the bottom of the image are the island ponds, A21, A20, and A19. And these ponds were breached back in 2006. And we can see in this picture, which is a few years old, that these ponds have accreted sediment. They've filled up. They're building marsh habitat. And they look quite different than many of the other ponds that you see in the background up here. So the project that we're going to be talking about is the A8 reconnection project, which includes pond A8, A5, and A7, and also pond A4. So it's kind of this whole region back here. When we first started doing the modeling for the island ponds in 2003 for Cargill, the modeling tools that we had to look at these ponds and how they were going to evolve were not really nearly as sophisticated as what we have today. And the questions that we were really looking at that time were, how do we get the high salinity that's in these salt ponds out without, hurting the environment? And the other biggest concern was there's a railroad bridge that goes right down here between pond 821 and 820. And there's concern and interest about the potential for scour in the channel due to changes in tidal prism and velocity. So when we did that project, we really focused on pretty limited things like salinity and the scour in the channel. From watching these ponds evolve and from developing better tools over the last 20 years, we can really ask much more sophisticated questions now and understand how designing these projects can help make them more successful. So because you can see right now that the A8 pond group is basically open water. So it's it's a deeply subsided pond. It operates right now as a muted tidal system. And we want this to evolve to be more like what we see here in the foreground for the island ponds. So today I'm going to first begin by giving an overview of the Calabasas San Tomas Aquino Creek-Marsh connection project. And I'm going to talk more generally about the role of modeling in project planning and design. And I'm going to give two different examples of modeling that we did for this project. One is detailed 3D simulations of sediment transport over relatively short timescales, less than a year. And the other is predicting long-term sediment accumulation and habitat evolution over the full span of 50 years. Before I begin, I just want to acknowledge Valerie Water, who is our project lead for this project. And also the project partners are U.S. Fish and Wildlife Service and the California Coastal Conservancy. The modeling part of this project is funded by CDFW through the Prop 1 water bond. All right, so now I'm going to just give a quick overview of the project. So this figure shows the Calabasas San Tomas Aquino Creek-Marsh connection project. This is looking kind of from the opposite direction as what the photo that we started with shows. So this is now looking at the bottom end of pond A8, pond A5, and pond A7. And it's called a Creek-Marsh connection project because there's 5 main creeks that flow in to the project area around pond A8 and pond A4. So we have Guadalupe River, San Tomas Aquino Creek, Calabasas Creek, the Sunnyvale East Channel, and Sunnyvale West Channel. Historically, these channels, particularly Guadalupe River and San Tomas Aquino, flowed into these marshes. However, when the salt ponds were originally diked off, the channels were levied and separated from the ponds and developed into the system that we have here today. And so one of the goals of this project is to reconnect these channels to the salt ponds to try and increase the sediment supply to the ponds, because right now a lot of that sediment is depositing in the lower reaches of the creeks. It needs to be removed periodically to maintain flood conveyance. So by reconnecting the channels to the marshes, we can create something closer to what the system was pre-disturbance, and also hopefully provide some additional benefits. In the context of the broader South Bay Salt Pond Restoration Project, you can see our project area located here, outlined in purple. And the island ponds that we were talking about at the beginning are these ponds over here. So the primary objectives of the project are habitat restoration. We want to try and improve the habitat in the ponds. We also want to achieve resilient flood protection. We want to reduce the maintenance needs in the channel, specifically the amount of dredging of sediment that's required. And we also want to enhance public access. The part that I'm going to be talking about today is this first part, really, the habitat restoration element, since that's most related to the South Bay Salt Pond project. So for the restoration project, we considered a variety of different alternatives and a variety of different features. This just shows some examples of different things that are included in the restoration elements that we looked at. One of them is breaches. So you can see here This is basically, punching a hole in the levee and allowing the tides to move back and forth. We consider placement of islands in the ponds to provide habitat and refugia. We also considered ecotones. So along the backside of the pond A4 and pond A6, you can see these transitional habitats can be created to provide habitat at a range of different elevations. We also looked at some alternatives that included gates and other features. So generally, I just want to talk a little bit about why we use modeling in these projects and what we can use modeling for. So in restoration projects, some things happen very rapidly. So this is a picture or two pictures showing the initial breaching of pond A17. So we have an excavator here that removed a section of dirt. We have the water from the bay rushing into pond A17, which was dry in the preparation stage. And we can see, there's water rushing in. The water's brown. It has lots of sediment. That sediment moves into the pond. It can deposit. And then as the tides reverse, some of that water is going to move back out. And so this type of process we can model with physical models that represent physical processes, hydrodynamic models, sediment transport models. We can represent the water coming in and out of the pond, the sediment being resuspended, and the sediment being deposited. A lot of the other aspects of restoration take place over much longer timescales, and it might look a lot more like this. So this is a marsh that is being restored, and we can see here there's also a lot of different processes that are going on that are taking a much longer timescale. So we still have water in the channels, there's sediment moving in and out, but there's also elements of the restoration related to the vegetation. So as the marsh plants grow, it generates biomass, and that also helps trap more sediment and lead to increasing the elevations within the ponds. The physical processes for modeling this type of restoration are much more complicated on longer timescales. And so to look at this type of modeling, we tend to use models that parameterize some of these processes and can be applied over much longer timescales so we can understand how the system is likely to evolve into the future. So I'm going to give an example of how we did some modeling to look at that as well. So one of the most useful things that we can do with models are to compare outcomes between different alternatives. So this isn't just an example that we'll talk about in a little bit, but we can look at, for different alternatives with different combinations of breaches, we can look at how much sediment from the bay can be deposited in each of the ponds and how much sediment from the creeks can be deposited in each of the ponds. And so you can see on some of these, we have breaches in different places. So in these two alternatives, we have a breach here in pond A8 that's bringing in a bunch of sediment to the pond. This alternative doesn't have that breach, and we see a lot less sediment coming in to pond 8. And we can look for each scenario, how much sediment is being deposited in the ponds due to bay and creek sediment under the baseline existing conditions and under each of the alternatives. And we can see that, breaching these ponds, connecting the creek can make a big difference in the rate of sediment accumulation in the ponds. And in this sense, the models are really useful because we can change locations of breaches, breach depths, and look at how that affects what's going to happen. These models are really useful for looking at shorter periods of up to a year, but we can't really run these models for a period of 50 years to predict how it's going to evolve longer term. We can also use models over longer time horizons to try and predict long-term outcomes. So right now, we're assuming that the project would start in 2030. And the current condition within the project area, basically all of the depths, except with the exception of some of the The margins are below mean low or low water. So these ponds basically are open water with a muted tidal system. We can look at different alternatives and different sea level rise rates, and we can try and project what the habitat might look like in the future for different scenarios. So we'll kind of walk through this example as well to see how we can use models to look at longer term outcomes. So first I want to talk about the 3D sediment transport modeling. So when we develop a model to do 3D sediment transport, what we're trying to do is represent as much as we can the physics of a very large and complicated system. And we do that by starting with basically what the shape of the landscape looks like, what the bathymetry looks like. And we can basically make a grid that represents the bay within all these little squares or triangles. And we do the calculations between each of these cells. And we can look at things like velocity, salinity, waves, sediment, and understand how these all change as the tides move back and forth. And the bottom panel just shows an example of velocity and salinity in this part of the bay. So we need to do this for the entire bay. And we can change the grid resolution as we do. So we can use coarser grid cells out into the ocean here, and we can use very fine resolution down here into the project area. That allows us to simulate the physics of the whole bay. So we can start with the tides at the Pacific Ocean. We have a whole large number of tributary inputs around the bay shown by the blue arrows. The model includes spatially variable evaporation, precipitation, and winds. These purple and red stations around the outside of the bay provide those. Within the delta, we have a whole number of operable gates and barriers, as well as hundreds of agricultural diversions and return flows. And so all of these feed into the model, and we can predict, over long timescales, the tides, the currents, the waves, and the sediment transport. Okay. When we start to look at sediment, we also need to link the hydrodynamic model to a wave model. So we need to predict the waves in the bay, because the waves are very important for simulating sediment transport. The programs we're using for the 3D sediment transport modeling is the untrimmed hydrodynamic model that you can see here at the top. For the waves, we're using the SWAN wave model. And for the morphology, we're using the sedimorph sediment transport model. So the sedimorph model sits kind of below the untrimmed model. So anywhere below the water surface, we keep track of additional layers of sediment. So every single time step, and we're running at a time step of 90 seconds. So we would every 90 seconds, we calculate out the waves and the hydrodynamics. We can compute the shear stress in any given cell. We compare that to the sediment in that bed cell. And if there's erosion or deposition, that sediment moves up into the water column or deposits on the bed. That actually changes the bathymetry within the model. So there's a direct feedback between any erosion and deposition occurs and the shape of the bay for the next time step. So for this study, we focused on a 6-month period, which spanned from December 1st, 2016 through June 1st, 2017. This is a portion of water year 2017. And this year was selected because it had a relatively high sediment load based on the last 25 years of records. This was the second highest sediment load from the creeks in the project area. So we wanted to be able to look at a period with high sediment inputs from the creeks and see where that sediment goes. So I'm going to start an animation here right before the red line shows kind of where we are in the animation. This red line on the other side shows the tides going up and down. The top left panel shows the concentration of sediment that's derived from the bay. And the panel on the right shows the concentration of sediment that's derived from the 5 creeks flowing into the project area. So when I start this, hopefully it's not too laggy over Zoom. But you can see here, um, initially, before these high flows start, we see large concentrations of sediment moving in from the bay into pond A5 and A7. We see much lower concentrations of bay sediment in the backside of A8. And we see not a lot of contribution of creek sediments. But as we move forward here, we're going to see a small flow and then some bigger flows. These result in some input of creek sediment. The vast majority of the creek sediment comes in during the high flows. So we can see even in this kind of moderate flow here, the sediment tends to be still dominated by the bay sediment because the South Bay has relatively high sediment concentrations, and this provides a good source of sediment into these ponds. So every tidal cycle, when the sediment comes into the ponds, some of that sediment deposits out, and then the water leaves with a little bit less sediment in it. We're going to have a large flow is going to start here in a second, and we'll see a very large pulse of sediment coming in. So you can see a very large flow event here. Very high concentrations of sediment come down the creeks during those high flows. And so you can see a large amount of sediment deposit moving into particularly pond A8, but also into the other ponds. So unlike the bay sediment that's moving in kind of every tidal cycle throughout the year, the input of the creek sediment is really focused on these big flow events. Okay. So if we get to the end of this simulation, we can look at where the sediment deposits based on where it originated. So on the left side, we have sediment deposition for one of the alternatives, showing the sediment that was either on the sediment bed initially or coming from the bay. And that's shown here on the left. And we see that sediment tends to be dominated in pond A5, pond A7, and some also here in pond A4 from the breach. Whereas the creek sediment, we're in this scenario, we're connecting Calabazas and San Tomas Creek into pond A8 South. There's a source of sediment to the ponds here. There's also sediment from Guadalupe River, comes down into Alviso Slough through the A8 notch and also through the breach here. And so we can see that the creek sediment tends to be dominated in the back side of pond A8, and the bay sediment tends to be concentrated here. If you look at this top graph, this shows a bar graph of the fraction of sediment predicted to be deposited that's bay sediment and creek sediment. And you can see in all the alternatives we looked at, including the baseline condition without the breaches, the dominant source of sediment to the ponds is the bay sediment. But there is a significant contribution of creek sediment in each of these alternatives as well. So connecting the creeks to the ponds does supply a significant additional source of sediment that wouldn't be there if we were only had the breaches on the bay side. So this example this explains this figure that we looked at the beginning, how we can use models to compare outcomes between different alternatives. In this project, we came up with an initial set of 5 alternatives. Based on that, we developed 2 more alternatives, and then we made another step where we even refined further those alternatives to try and achieve as many of the project goals as efficiently as we could. And because in the model, there's obviously some uncertainty in the predictions. A lot of that uncertainty is the same for all the scenarios. So it's really good in being able to compare different outcomes for different alternatives. Okay. Now I'm going to talk about the other type of modeling we did, which is quite different. And this is long-term habitat evolution modeling. So the model that we use for this is the warmer model. It's a 1D model, not a 3D model like the hydrodynamic sediment transport model, but a 1D model. And it only operates really in the vertical. It's just a vertical model. It tells us each time step what the rate, the relative rate of sediment accumulation is relative to the relative rate of sea level rise. The model incorporates both biological and physical processes, and it gives us an annual vertical rate of marsh accretion. Even though the warmer model is only really a 1D vertical in a single point, we can apply it spatially by basically running it a whole bunch of times using the initial elevations across a wetland. And this can kind of give us a 2D map of how the marsh evolves, but it doesn't take into account any of the horizontal processes. So the warmer model doesn't see where there's breaches, where there's channels, how close you are to an island, or any of the other aspects of the 2D the warmer model doesn't see. And so the conceptual model is we're incorporating all the different processes that can affect the elevation change within a marsh. And the arrows to the left mean that it's reducing accretion, and the arrows to the right mean that it's increasing accretion. So relative sea level rise, it's making the water level increase relative to the marsh, so the water level is getting deeper. Productivity goes in the other direction, so organic growth. Sediment input, primarily from the base sediment. Root growth is also a source of biomass that helps to increase the accretion rate. And there's two negative terms for compaction and decay. And all of these are parameterized based on observations made in the field at other marshes in the vicinity of the project. So we're using a lot of the data from the Swanson et al. Work from 2013 and 2014 in Loudmeister Marsh and Whale's Tail Marsh as being an index site for this project. So we did do something a little bit different in this project, which we used the warmer model in combination with the results of the short-term 3D sediment transport simulations to predict the future marsh conditions. And so how that looks is we basically are adding another input to the model. So warmer doesn't know that we've added these breaches or that we've connected these creeks and that we're adding this additional source of sediment supply. It's really using a sediment input that's based on the sediment input that's being achieved at nearby fringing marshes to the bay. But we're going to augment that by adding this additional creek sediment. So the way that we did this is, so we have this map, and this is what we predicted for 2017 for a 6-month period. That 6-month period included about 98% of the sediment load for 2017. And so we can scale that up slightly to say this is what the amount of sediment that would come in for 2017 would be. And we can add that into the warmer model, and we can do it spatially. Since we're running warmer kind of in each grid cell there, we can also spatially add this distribution of sediment accumulation so that the effect of the creek reconnection isn't uniformly spatial. It actually takes into account some of these 2D effects. So we also know that not every year is as wet as 2017 was. And so 2017 is over here. It has the second highest sediment load of the 25-year record that we have from the watershed model that SFEI developed. So we wanted to predict out 50 years into the future what the predicted habitat change would be. And so we used this 25-year record repeated twice. And we scaled the sediment predictions for 2017 to mimic the sediment loads from all these different types of years that we had. So the sediment supply varied from about 4.2% to about 132% of the predictions for 2017. So warmer steps through time annually, and each year we added one of these sediment loads to the accretion of the marshes. And so that takes into account the annual variability, and then it gives us a picture over a long time about how the combination of creek input of sediment would affect the evolution of the marshes on a longer timescale. The other important aspect of doing the modeling with warmer is to evaluate the effects of sea level rise. So for our project, we're assuming a 50-year planning horizon with the project construction beginning in 2030. And we're looking at the evolution of the marsh within the project area from 2030 to 2080. So the Ocean Protection Council developed a California sea level rise guidance, and there's some great tables for different locations. This shows the location for San Francisco, showing the sea level rise in feet since 2000. For our work, we selected two of these scenarios. The intermediate low scenario, which is considered to be probably the most likely, is 1.2 feet of sea level rise by 2080 relative to 2000. And then we bracketed that with the intermediate high sea level rise rate, which is 3 feet of sea level rise by 2080 relative to 2000, or 2.6 feet of sea level rise between 2030 and 2080. So this shows the relative sea level rise since 2000 for the intermediate low curve. It's a slightly climbing rate, and the intermediate high, which is a much steeper rate. And so when we look at habitat evolution in the face of sea level rise, we also have a moving target for what the habitat is, because as sea level rise changes, mean lower low water increases, mean tide level increases, mean higher high water increases. So as we look at marsh habitat within certain elevation bands, those bands are changing over time. And as sea level rise is faster in the intermediate high scenario, those bands are moving up faster too. So we have to have much higher sediment accretion rates to be able to keep habitat in those areas. So this shows the initial condition that we used for the warmer model, showing the initial pond elevations in 2030, shown here. We can see all of these are generally negative relative to NAVD 88. So these are all below mean lower low water when we map them out based on the current tidal datums, with the exception of some small amounts along the edges of the ponds. And part of these are the assumed constructed ecotones that would be built along the south end of Pond A8 and Pond A4. So I'm going to step through by decade here the predictions of the habitat evolution. What we're seeing on the left is if we just run the warmer model by itself with no additional sediment input from the creek. So this would be kind of if we breached Pond A8, but we didn't do the marsh connection project, what would it look like? And on the right is the process that we talked through in the previous slides, where we combine the warmer predictions annually with an additional load term that's the input of the creek sediments. So in 2040, we can see a little bit of the area, especially around closest to Pond A6 here. In Pond A5 and A7, we have some areas that are moving above mean lower low water into this next blue band. And at least to my eyes, these look really very similar. There's not a lot of difference between these two in the first 10 years. And a big part of that is because a lot of this area is starting well below mean lower low water. So even it takes a while just to get up to mean lower low water. We step through in 2050. We can see, largely because of the contribution of the base sediments, we're seeing Pond A5 and A7 with filling up and accreting. There's more of that area between mean lower low water and mean tide level. But we are also starting to see some differences down here in Pond A8 that result from the contributions of the creek sediment. So you can see more areas near this breach, and also in Pond A8 South, where we have habitat moving up above mean low or low water. By 2060, again, Pond A5 and A7, where we didn't see a lot of prediction of creek sediment, they look pretty similar with and without the creek sediment. But even, there is some additional accretion of creek sediment that's showing up in Pond A5 and A7. But we do start to see more habitat development here in Pond A8 and Pond A8 South, and these are the deepest areas to start with. So these are going to really be the hardest ones to get sediment accretion into. By 2070, we see, with the creek sediment, much of this pond is accreted to above mean tide level, and some areas in the mean high water to mean higher high water. And we do start to see, even in Pond A5 and A7, more areas in that higher elevation habitat than we have if we don't do the creek connection. And this is showing conditions for 2080. So does start to be a pretty noticeable difference in these scenarios, particularly for Pond A8 and Pond A8 South. The outcome looks quite different by including the contribution of the creek sediments. And so this really highlights, how important it is to be able to look at spatially how these projects evolve and how we can improve them. Because I think one of the challenges for Pond A8, because it is deeply subsided, is how to get enough sediment into Pond A8 to help bring it up to marsh elevation. So this is for the intermediate low sea level rise. And I'm not going to step through time for the other sea level rise case, but I will show the ending state. So this is intermediate high sea level rise case. And when we have intermediate high case, the sea level rise is rising much faster. And so the rate of accumulation of sediment has to be much faster in order to keep up. So we see in the non-connection project, where we just breached Pond A5, A7, and A8, a big portion of Pond A, well, pretty much all of Pond A8 and portions of A5 and A7 are still below mean tide level in 2080. So we haven't achieved all of the marsh habitat that we would want. With the creek connection, we still have areas below mean tide level, but we do see a larger amount of marsh habitat developing into the future. So for both sea level rise rates, we do see a noticeable effect of including this additional sediment from the creeks into the analysis. Okay. So this brings us to the other type of modeling that we can do, which is really to use models to predict long-term outcomes. And so in this case, we can say, well, this is the habitat that we have right now. And based on the alternative that we're looking at for the Marsh Connection project, we predict that the habitat will look something between this and this in 2080, depending on the rate of sea level rise. So for something like an intermediate low scenario, we expect much of this habitat to evolve to be between mean higher water and mean higher high water by 2080. And with a higher rate of sea level rise, we're looking at not achieving that level of marsh habitat, but still having the majority of the ponds accreted to above mean tide level. Okay. Just have a couple closing comments and then move on to questions. In this project, modeling was used to analyze and refine alternatives, and it was also used to help select the recommended alternatives. There were, as we talked about at the beginning, there were a number of other aspects of the project, such as maintenance, public access, that were also included in the evaluation, but modeling was an important tool that helped us evaluate and select between the alternatives. The sediment transport modeling showed that while the deposition in the pond group was dominated by the bay sediment, creek sediment was also a large component of the deposition in Pond A8. The long-term marsh accretion modeling that we did with Warmer showed that the Creek-Marsh connection accelerated the rate of marsh habitat development, particularly within pond A8. And because of this, the modeling for this study shows that reconnecting the sediment supply from the creeks to the tidal wetlands contributes to ecosystem resilience. And as we look at higher rates of sea level rise into the future, capturing these sediment supplies and contributing that additional sediment to the marsh can make a big difference in how well the marshes can keep up with sea level rise. And with that, I'd be happy to take some questions.
Well, that was excellent. Thank you. I have a whole bunch of questions I wrote down, but I'm not I'm not in charge of this. So I'm gonna step
I think
back and
you
see
are
if
in charge
they're
of this, Dave.
well in charge of it. I'm not, this isn't for me, right? This is for our audience, our guests. So I mean I should open up the floor to some of them. I see one question in the chat from Kat. Do you want to ask that directly? Maybe this even got answered as we went.
I did answer that one
Yeah.
as we
Yeah, I thought so. Yeah. So short of that, questions from the audience,
Um, I have a question.
please.
This is Stu Weiss.
Hey, Stu, how are you?
Hi, I'm good. I'm curious about where the source of the sediment is coming from, whether it's the urban areas or the kind of suburban areas or the more wildland uh, upstream.
That is a good question. I think it's probably a combination of all of the above. For us, the source of the sediment is the watershed model that SFEI developed. They did a study where they looked at all the watersheds around the bay.
Okay.
And based on the watershed area, land type, runoff, dams, they estimated the sediment supply, from each of the creeks. I believe there were daily values of sediment loading. So there is actually a really good report that SFEI developed that talks about that sediment supply.
Hey, thanks for that lead.
Yeah, so Stu, you were looking for the source of the data for the input, not like what the
Well,
physical source of the
I'm just
sediment
interested.
is, right?
Yeah, well,
Right.
no, I'm interested in like, the what that study showed where the sediment is coming from.
Yeah.
This is for the third version of the Bay Area Conservation Lands Network, and we're trying to do connections from the uplands to the baylands and vice versa. And it's just great that SFDI has some ready-made numbers.
Yeah, they're actually really helpful because they did it for the entire bay.
Yeah.
And Scott just chimed in that SFEI is also just starting a sediment source assessment for the San Thomas Aquino Creek watershed that will be completed next year.
Hey, thanks.
Well, Michael, you appear to be looking at the chat. So you see a question there from Chris Janisak. Chris, do you want to elaborate at all, or is your question self-explanatory?
Yeah, I think it's pretty self-explanatory. I'm just wondering if you had scenarios, because I guess it looked like from your maps that the restoration scenarios you looked at were punching holes in different places at these sites. And I was wondering if, and maybe it's an engineering nightmare, but removing much larger sections of the levee to kind of allow more sheet flow in and out of these systems.
We did look at one alternative that had a berm lowering along pond A4. But largely we focused on the breaches relative to the berm lowering. I think from an implementation and cost standpoint, it's a lot more cost effective to open up a breach, and then they tend to self widen relatively efficiently. It's pretty expensive and difficult to get equipment out and do large scale work on the berm lowering. Is my understanding. That's not my exact field of expertise, but it is more complicated and expensive.
I see a question from Christina Toms. Hello, Christina. How have you been?
Hi, everyone. I've been well. I hope you're all doing well. Hi, Mac. I have a question about sensitivity of the modeling and sort of base conditions. My understanding, and I'd love to hear if I'm wrong, particularly from you or Dave, is that we've never had a super high accuracy picture of sort of base elevations and bathymetry and topography in a lot of these ponds. And it seems like from the combined modeling that, sort of your starting elevation, right? Like with the warmer model, that initial ground elevation is really important. And so I'm wondering, so I guess my first question is like, A, how much of that really is, or maybe the broader question is, have you done a sensitivity analysis to see how the longer term results would vary if you were to make slight changes to baseline topography, to suspended sediment concentrations coming in from the base, sediment that's coming in from the watershed? Because it really looked like so many of those alternatives really were just kind of within a certain margin of error, right? So what happens if we change some of these input variables?
I'm going to jump in and just before Michael elaborates on the sensitivity analysis part, I just to answer this one thing that um, I think in preparation for this project, Valley Water did fund a pretty extensive and detailed bathymetric study inside of the A group, so A5, 7, 8, and
Oh,
8 South,
cool.
and that was done in 2020. And Judy's here and can answer any questions you have about that specifically, Christina. But like that input data was pretty strong and pretty recent. Your sense is right that we don't have that at that level of detail and currency across the entire restoration project, but we have it here thanks to Valley Water's efforts. So
That's awesome. That's great to
so
know.
now Michael can cover the rest of that question.
And they also re-surveyed Pond A4 as well, so we got good
Ah,
bathymetry for Pond A4. Yeah, I mean the results are sensitive to obviously the initial starting elevation. They're sensitive to the assumed sediment input. One thing that we did look at is when we did the initial warmer simulation kind of for 2030, we compared the predicted marsh accretion from warmer for 2030 to the predicted accretion from the untrimmed sedomorph model for that first year that we simulated, and they were within I think about 8%, which is really remarkably close in terms of like how much sediment accumulation of base sediment did the hydrodynamic model predict in that 6 month scale to a year versus how much sediment accumulation in those ponds did warmer predict in that first year, and they were pretty close. But they're the models are pretty sensitive to that. But the good thing is we do have data, and the sediment accumulation rates and the organic production rates that we used in the warmer model were developed from the marshes quite close to this site, and that's I think one of the big things that help. There was another question here about have you applied the untrimmed warmer approach to hindcast long-term bed changes to any recent restoration projects, e.g. A6 or the island ponds from Matt Brennan? So we actually did simulate back in, I think about 2012 or 2013 with untrimmed sedomorph modeling of the first year following the A6 breach. And John Calloway collected, I forget the exact number, but around eight, he had about 8 pins out there where they went and measured the sediment accumulation over the first year at various points. And the on average, the model did a pretty good job. I think there's about 20 centimeters or so of sediment accumulation over that first year in Pond A6, and the model predicted that pretty closely. We haven't, this is the first time I think we've really done a kind of coupled untrimmed warmer approach in the sense of using the additional sediment inputs from the creeks, but I think this is also the first time that we really tried to tackle what the implications of connecting the creeks to the marshes would be. So I don't think we have great data yet to validate that.
so Michael, you see the question here from R.H. Chelsky, and I sort of had a similar question. So, Ari, do you want to elaborate or frame up your question, or should
Yeah,
Michael
I
just
guess
read it and answer?
yeah, well yeah, I think Michael just showed like different
Yeah.
alternatives and they seemed like a lot of them had maybe similar impacts on sediment accretion using the 3D model. And I was just curious if you yet like use this model to test these different alternatives. And you mentioned in the summary that I think you selected one, or maybe you made a recommendation for which was most beneficial for sediment accretion. I was just curious what that was.
Yeah, actually, the alternative that alternative 6 actually was the one that is moving forward as the selected um, alternative at this point. We went through an entire kind of multi-year exercise looking at sediment, water quality, salinity, access, construction costs, maintenance needs, scour, kind of all those different elements of the project um, in helping to select the alternative. And those have all been presented at various public meetings and forums. I think a lot of those meetings are also recorded and potentially available to watch online. Maybe Judy can answer that. I didn't want to just do a presentation of like, here's 5 alternatives that we looked at and kind of, why we picked what we picked. I wanted to do a little bit more general presentation on some of the why behind the modeling, but there is information available on the different alternatives and why the selection has been made the way it was. I don't know, Judy, if you want to say anything more about that.
Yeah, I was just going to invite Judy to elaborate on that if you wanted. I was a part of those processes too. They are all published in different Valley Water, work products that are available if anyone would like to see them. Judy, I'm tap dancing to buy you time to unmute yourself if you want to jump in.
Sure. Sure. Thank you so much.
Yeah.
Yeah, so I just wanted to let you know that there's a project website and we had multiple, public meetings and whatnot going through sort of the decision process of how we arrived at alternative 6 and, presented, in different juncture, like, what are some of the consideration? Obviously, the project objectives that Michael talked about, those are sort of based on which we kind of, decided on considerations and after, thorough consideration, arrived at the alternative 6. And, just one of the, big consideration was once again, building the tidal marsh. And as, he was able to demonstrate that, allowing that creek sediment coming in and, southern portion of the A8 was a really important aspect, knowing that project objective is, habitat restoration. So I think that was one of the big contributing factor of arriving at that particular alternative. But I'd be happy to share the project website, and there are all these documentations, and then I think the meeting presentation slides and whatnot, those informations are available. So
Yeah.
I'm happy to share.
I appreciate you doing that, Judy. If you want to drop that website in the chat, that would be great.
Sure.
Otherwise, we can send it out after, I suppose. But just to elaborate both on where Ari was going, but also Chris Janicek's question about these, like, why not just more and larger breaches and lowering sections of levee down to marsh plain elevation, even if they're not all the way down to the the invert elevation of the surrounding sloughs and things like that. And I mean that all of those things were looked at in some measure in that analysis, development, and screening process that the Stillwater team worked on. If you were only optimizing for one thing, you might do that, right? But we were also optimizing for things like construction cost or maintenance cost, or not increasing upstream flood risk, or not opening up too many things on the west side of the A group, so that the nutrient-rich water from the Sunnyvale wastewater treatment plant didn't go straight into these ponds and have a long residence time in there. So there's all these really complicated balancings that the project team was thinking through, evaluating in both developing the initial set of alternatives of, I think there were 20 at first, and then that went down to 5, and then Michael modeled 5, and then there was a few extras added on. And so it's been quite a lot to even get to sort of a recommended alternative. So that's my little editorial on that. But I have been very curious about, like, what would happen if you just took down 50% of the levees, for example, right? And that's an expensive and difficult modeling effort that I don't think we've done yet. But it may be possible to add more of those construction cost, or I guess reduce the weight, the influence of construction costs by, if we chip in later, maybe we do a few more things and get a little more circulation and a little bit faster accretion. So I'll stop there, but see if
Yeah.
anyone else has any
And
questions.
actually,
Yeah.
one thing to add to that, a couple people noted that the sediment accumulation seemed relatively similar between the alternatives. And regardless of the number and position of the breaches, one thing that all the alternatives had in common was that the total width of the breaches was enough that we achieved the same tidal range. So we didn't want to have a muted tidal pond. We wanted to open up the breaches enough that you have the same filling and draining of the pond, and it's not constrained by the breach widths. And so in the sense that the amount of sediment that's deposited in the ponds is largely going to depend on how much water is coming in each tidal cycle and then dropping out and then leaving. That tidal prism was basically the same for all the alternatives. And so lowering more berms wouldn't bring in more water each tidal cycle, because we're already kind of really achieving the same tidal range within the pond that we're achieving in the creeks adjacent to the ponds at that point. So there is kind of, in a sense, limited additional value of lowering those berms. And the other aspect of those berms that people thought was important was each of those berms, once you make multiple breaches, the section of berm between two breaches is basically like high tide refugia habitat that's not connected to land. So rather than building islands, those berms are islands that provide some of that habitat.
That's right.
Feature there as well. So even in just kind of they provide a very different ecological function once there's a piece of berm that's between two breaches that's not connected to land anymore. It has a different ecological function that's important.
That's an excellent point and a good refinement on mine. It's 11:59, so I just gonna ask this one question that DB Loy put in the chat here about the start date. And he thought it was, or she thought it was 27, and you said 30. I mean, that's kind of an assumption anyway, right? That's not known when construction will finish.
Yeah, maybe Judy can speak to that. I can say that for whatever reason, the OPC published their sea level rise rates by decade. So it made the most sense for us to start on 2030 as the kind of this sea level rise to start from, and ending at 2080. Obviously, we could kind of shift a little bit and interpolate. But that was, part of the logic behind that. But, there was some discussion of like, is the start date 28, 29, 30?
Yeah.
Maybe Judy can speak to that. But,
Yeah, Michael, thank you so much. Yeah. So there, this project is right now at the sort of the tail end of the planning phase, where we're doing the PSR and planning study report and wrapping up. And as we are moving into a design phase, I think we're going to probably update the schedule. And one thing that I want to emphasize is there is no secure construction funding for this project as we speak. So really depending on, there's a lot of still kind of uncertainties involving, construction start. So as we are working very hard to secure the, grant funding, and I think Dave was talking about how we were so fortunate to have bathymetric survey and all these ponds, and Pond A4 was funded by the Measure AA, grant. So this project's been very successful getting grant funding, and I'm hoping we could, continue that successful effort in, securing the construction funding as well. So that, exact year is going to be, something we would have to continuously work on, and hopefully we could expedite with our successful grant funding in the future. Thank you.
Nice. Thanks for that, Judy. Thanks to Michael for an excellent presentation. Thanks to you all for being here and for the good questions and discussion. I appreciate everybody's engagement. And we will have this posted on the website within a day or two. Both the deck and the recording should be there. So check it out, download it if you need it, share it with your friends. Thanks to Donna for putting together the Lunch and Learn Science series all year, and to SFEI for all the tech support and hosting, and for all the interest and speakers and guests. Really appreciate it. Have a great afternoon, everyone.
Thank you, Dave.
Mhm.